Selamat pagi Bu Ririn.
Assalamualaikum Mbak Trianda.
Salam. Alhamdulillah bisa join Bu. Nggak ada
Oke.
jadwal mengajar kok Bu.
Ini lagi ada kegiatan workshop, jadi enggak di kantor.
Oh, sudah boleh daftar
Workshopnya,
keluar ya Bu ya.
iya, workshopnya di luar, tapi ternyata disuruh daring. Lah aku ini dilebokno nang hotel apa?
Di kamar di.
Jadi habis sarapan terus balik nang kamar. Mak lucu aku nih. Makar ngono lak nang omahe ya.
Mas tadi mau lift Pak?
Maulidnya kemarin.
Oh, iya. Lift maksudnya. Lift. Mau lift. Selamat pagi Prof. Redi.
Assalamualaikum Bapak Ibu semua. Mohon maaf karo jalan soalnya saya dari
Waalaikumsalam.
handphone. Jam berapa mulainya?
3 menit
Jam
lagi.
10 harusnya.
Jam 10 ya. Ini kan acaranya Pak Menteri bisa soalnya.
Oh iya ya, pamerannya.
Iya wes tak serahno Pak Dekan aja sing ngono-ngono iku. Saya tak ngurusi kisik.
The world keeps evolving. The times keep changing. The new generation of technology. The new generation of information. They bring the future before us. Institut Teknologi 10 November, a place where the spirit of heroism underlies the new generation to research and innovate in technology. The University of Heroes, ITS. ITS is one of the best science and technology universities in Indonesia, which was founded by Dr. Angga in 1957. In every step, ITS focuses in advancing education, research, management, and community service. As an incorporated public university, ITS has been able to manage autonomously the policy of academics, organizations, finance, students' affairs, human resources, facilities, operational, and infrastructure.
In the spirit of Indonesian heroes, during the battle in the 10th of November 1945, ITS always makes efforts to be the best in education, research, and community services, especially in the fields of industry and maritime. ITS also actively contributes to the nation development, and in the future, ITS will become an entrepreneurial university with world-class reputation.
ITS has many achievements. Both national and international achievements prove that ITS keeps growing and gives the best contribution to the nation of Indonesia. ITS is a place for new hopes to grow. An ideal environment for the new generation to flourish in 3 strategic locations within the industrial city of Surabaya. As a smart eco-campus, ITS maintains harmony between technological advances and the sustainability of the surrounding ecosystem. ITS has 7 faculties with prospective scientific fields, including Scientics, INSIS, Vocation, Creatis, Martech, Electics, Plan, Interdisciplinary School. ITS is a space for the new generation who are hungry for knowledge because it provides a wide range of references in both physical and digital form. ITS makes it easier for the new generation to access information by providing flexible classes. ITS keeps moving forward in facing future challenges by providing the best facilities for the new generation's activities. The facilities support both spiritual and physical needs. ITS also provides research facilities in the ITS Science Technopark, including ICT and robotics, automotive, maritime, and creative industries. Therefore, the excellent generations from ITS will emerge and make history. ITS is a space for the new generation to express themselves. ITS is a place where the new generation learns.
Thank you. Okay, thank you, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good morning, ladies and gentlemen. My name is Tamam. It is a wonderful and precious chance for me to be your master of ceremony in this beautiful morning on Tuesday, 21 October 2021, in our fantastic event, International Seminar with the theme Progress in Membrane Ceramics for Full Cell Application. First of all, let's say thanks to Allah Subhanahu wa Ta'ala, who has been giving us guidance, happiness, healthy, and mercy, so we can attend and participate in this event without any obstacles. Praise and salutation upon our Prophet Muhammad Sallallahu Alaihi Wasallam, the best figure of this universe, the person who was able to save us from the Jahiliyah era. In this beautiful moment, I would like to welcome Prof. M. Hafiz Darzan Othman, who will be the speaker at our event today. The Honorable Prof. Hamzah Fansuri, MSc PhD, President of the Faculty of Science and Data Analytics. The Honorable Prof. Dr. Renat Freddy Kurniawan, MSc, as Chair of the Chemistry Department. The Honorable Dr. Trianda Gunawan, SSE, as moderator of this event. Once again, we thank you for the presence of Mr. and Mrs. Lecturer. Welcome to all participants of the seminar present today. Ladies and gentlemen, before we begin this event, let us pray together by reading the Al-Fatihah letter. May Allah Subhanahu wa Ta'ala make this event beneficial for all of us, and this event can run smoothly and conductively. Start praying. Finish. On this special morning, we have several agenda. So allow me to read several sequence of our agenda. The first is the opening, which we previously had read together. The second is singing Indonesia Raya and ITS hymn. The third is remarks. The fourth is the core event, seminar about progress in membrane ceramic for full cell application. The fifth is closing and prayer. Step on the following agenda is singing Indonesia Raya and ITS hymn will be led by our operator. Time is yours. Thank you for all. The next agenda is remakes. Ladies and gentlemen, I immediately invite the chair of the chemistry department to Prof. Dr. Renat Freddy Kurniawan, MSc, give his remarks. Time is yours.
Okay, thank you very much, ladies and gentlemen. The honorable speaker, Professor Muhammad Hafiz Darvan Uthman, and the Honorable the Dean of FSRITS, Professor Hamzah Banturi, and our beloved student which attend to this event. I welcome all of you in this event. Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, today is our second international seminar on chemistry department, which is will delivered by our special guest, Professor Muhammad Hafiz, is one of our adjunct lecturer, adjunct professor in chemistry department. The first one is which have delivered the seminar was Professor Masato Taminaka from Saka University. And this one, we have our colleague from Malaysia, Malaya University, if I not make a mistake, will deliver in topic which is connected with about fuel energy. And we enjoy this session until the end, and please stay in this session until the end, because today we also have one of Ministry of Education, higher education in Indonesia, with visit in ITS also. So we have many activity today, and I hope you will stay in here until the end. Thank you very much for your attention. Please enjoy this session until the end of the event. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much to Prof. Dr. Renat Freddy Kurniawan, MSc, for the remarks. Let's keep on the next agenda, core event that is switched. I give it to Dr. Krianda Gunawan, SSE, as the moderator to lead this fantastic event. Time is yours.
Okay, thank you very much, Pak Tanam, for your kind of introduction. Good morning, everyone. Good morning, Prof. Hafiz.
Morning.
Nice to meet you, Prof. Okay, so today we welcome you to the...
I cannot hear you very well, Dr. Triana. I'm not sure whether the rest can hear you or not. Yeah.
Okay, just wait a moment. Okay, 1, 2, 3. Is it?
Yeah, this is better. Yeah.
Okay, thank you. Okay, good morning, Excellencies, distinguished guests, ladies and gentlemen. Welcome to the International Guest Lecture. Today's topic will discuss about progress in membrane ceramic for fuel cell application. Dear ladies and gentlemen, some of you who are working on this field or maybe begin to work in this field probably curious. Maybe there are some questions like, what is fuel cell membrane? How does it works? What is the current status of the fuel cell membrane? Well, today we have the right person to discuss it. Our spectacular speaker has already prepared all of that for us. I'm gladly introducing to all of you Professor Muhammad Hafiz Darvan Uthman. He is the Director of Higher Institution Center of Excellence of Advanced Membrane Technology in University Technology Malaysia. I myself have already met him in person, and he is a very nice and a very good in this field. Okay, before we start, let me read a brief about today's session, a brief proof about today's session, as well as I will give a brief CV of Prof. Hafiz. Okay, first of all, Prof. Hafiz, we apologize. It should be Prof. Hamzah that should be as moderator, but at the same time, he has another agenda, so I will substitute him instead. So today's webinar, we have some protocol. Please make sure adjust your name using the format name underscore campus. And please turn off your microphone during the lecture session. You might turn on your camera, so it will not feel lonely here. And please adjust your seat position comfortably and prevent the backlight effect. And ensure your network has stable internet connection. Furthermore, we would like to inform you that we also live stream this session into the YouTube of the faculty channel. And later on, we will give you the link if you are more comfortably joining via YouTube. Okay, so the next is the CV about Prof. Hafiz. Prof. Hafiz got his Doctor of Philosophy in Imperial College London back in 2011. He is now a professor, full-time professor in University Technology Malaysia, as well as a director in Advanced Membrane Technology. Okay, next. He received a lot of awards and fellowship. The recent award he got from the Japan Intellectual Property Association Special Award for the Best Innovation for Environment Technology, Malaysia Technology Expo or MTE into 2020. For the project leader for the innovation entitled Hybrid Photocatalytic Membrane-Based Water Filtration for Persistent Organic Pollutant Removal. He also has numerous publications related to the membrane as well as to the inorganic material. So, Prof. Hafiz, are you ready for today's session?
Yes, Dr. Trianda.
Okay, good. Professor Hafiz will deliver his lecture for the next 40 minutes. In the time being, all participants who has any question can write it down in the chat Zoom. After the Prof. Hafiz deliver his lecture, we will have a direct Q&A session for about 20 minutes. At the session, you might ask directly to Prof. Hafiz if you have any. Please use first raise hand feature first. Okay, thank you, Prof. Hafiz. The screen is yours.
Thank you so much, Dr. Trianda Gunawan, for the kind introduction. I hope you can hear me clear, yeah?
Yeah.
Okay. Thank you so much. Thanks to all audience for your attendance today. And first of all, allow me to express my gratitude to the organizing committee, especially to Prof. Hamzah Fansuri, Prof. Freddy Kurniawan, Department of Chemistry, Faculty of Science, and also Institute Technology 10 November, for inviting me to give a lecture. This is the title of my lecture today. So I'm going to give a talk on the progress in ceramic membrane for future application. So my name, as has been introduced by Dr. Trianda, Muhammad Hafiz Afan Otsman. I'm from Advanced Membrane Technologies Center, MTech UTM. This is our building. Like been mentioned by Dr. Trianda, MTech is one of higher institution center of excellence, meaning that it is a national center of excellence in Malaysia. So the only research center in membrane in Malaysia as well. So if you can count, there are only 2-3 research center in membrane in Southeast Asia. So MTech is one of them. So probably you quite familiar with the name of the membrane when we talk about membrane. So probably you can imagine the membrane normally being used for the water filter, for the gas separation as well, right? So when we talk about membrane, we always associate it with the high cost. In Malaysia also, we not many industry try to avoid to use membrane. Yes, can you hear me?
Yeah, that was glitch for a second, but it's okay.
Yeah, I stay in the first slide actually.
Okay.
I'm sorry. So we always say, look, membrane very expensive. Okay, this make the membrane is not widely applied in industry. So people might wonder what make membrane expensive. So if you would like to know, one of the reasons why make membrane expensive is because of the sophisticated technology to fabricate the membrane structure. So what make membrane different than the normal coating layer? So membrane, if you can see from this slide, it has a narrow pore size distribution. It has a narrow pore size distribution, meaning that their pore size is almost equal throughout the surface. It's not like the normal coating layer. If normal coating layer, normally the pore size distribution is very broad. Okay, so when it's broad, it don't act as the selective barrier. But because of membrane, it is narrow pore size distribution, it's hard to be produced. Therefore, the cost of membrane normally is quite expensive. So due to its narrow pore size distribution as well, it makes membrane as the selective barrier, meaning that it only allows certain constituents to pass through and it will retain the other constituents. Okay? So the concept of a membrane is quite straightforward. This is, like we said, a conventional mechanism of membrane, meaning that it's based on filtration. So membrane will allow a small molecule, then it pore size to pass through, and it will retain the bigger molecular size on the permeate side. Okay, on the retentate side. So therefore, the membrane, the pore size of the membrane is really important to make it very selective in order to increase the separation efficiency. And if you can see the classifications of the membrane, the most common types of membrane is these 4 types: microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. So the ultrafiltration is the biggest pore size of membrane, from 0.1 up to 3 micron, followed by ultrafiltration, 30 nanometer up to 0.1 micron, and nanofiltration bigger than 1 nanometer, lesser than 20 nanometer, and the reverse osmosis, it is the smallest one, from 0.1 up to 1 nanometer. It's very, very small. Therefore, for reverse osmosis, it can reject all the molecule in water. Only water can pass through, because the good thing about these contaminants in water, it has a bigger molecular size compared to H2O. So H2O has the smallest size. So only H2O can pass through and it will retain all the minerals, all the contaminants on the feed site. People might ask me, what is the difference between membrane and other filtration process? For example, you probably have heard about cartridge filter, sand filter as well. So these types of filter, normally their pore size is bigger than 5 microns. But the membrane, on the other hand, is lesser than 3 microns. So it may make the membrane have to use a higher pressure compared to the sand filter. Normally, you probably can see that the sand filter, sometimes they use gravity only, right? They don't apply any pressure. So because of its pore size is quite big. But for membrane, normally you have to apply at least 1 to 2 bar pressure in order to make the fluid flow across the membrane. So when we talk about the types of membrane, so this is the classification that normally been used. It's based on the material that been used to fabricate the membrane. First, we have the organic membrane. Organic membrane is a either made from natural polymer or synthetic polymer, and it is the most commercially available in the market. Okay, so we also have another types of membrane, which is what we call as the inorganic membrane. For the inorganic membrane, we divide into three. Either it's ceramic membrane, carbon membrane, or metal membrane. Okay, and the commercial one is actually made from alumina and zirconia as well as titania. This is the common material for inorganic membrane, which fall under the category of ceramic membrane. And there's a new types of membrane. It's not so new, but it has been invented probably a few decades ago. What we call as a mixed matrix membrane. Mixed matrix membrane actually is combinations of the polymer and the inorganic membrane in order to cater the disadvantages or the drawbacks of both material. So when we mix together, we expect there is some synergical effect between the polymeric and inorganic combination. So that's what we call as the mixed matrix membrane. But for the mixed matrix membrane, it has not much been commercialized yet due to its leaching problem and also the agglomeration issue. So the two most common membrane in the market is a polymeric and ceramic. Okay, so for ceramic, it has advantages in terms of its superior mechanical strength, its good chemical and thermal stability. It's because of the nature of the ceramic itself is very, very tough. Okay, therefore, the ceramic membrane can be used longer operation lifetime. Normally, we can use ceramic membrane up to 20 years compared to the polymeric membrane. It's degrade over the time, and therefore we have to replace it periodically. Normally, from a period of 2 years up to 4 years, we have to change the polymeric membrane. But the main shortcomings of ceramic membrane is very expensive and is brittle. Therefore, because of these two drawbacks, it makes the ceramic membrane lack of the operational experience in industry. People tend to use polymeric membrane instead of ceramic membrane because of its expensiveness and also its brittle issue. The most common structure of asymmetric we call as the asymmetric structure. The common structure of ceramic membrane we call as the asymmetric structure. So asymmetric meaning that the top and the bottom layer doesn't have the same structure. Okay, this normally consists of several layers or more or one different ceramic material. For example, if you have the thickest layer, it's the porous layer that will give the mechanical strength that can make as a support for the membrane. And after that, followed by one layer as the intermediate layer. And after that, you have to coat a separation layer in order to alter the pore size of the membrane. For example, if you would like to produce microfiltration membrane normally is quite big pore size. So probably 2 layers, the support layer and the intermediate layer is enough to make the pore size within the range of microfiltration. But in order to further reduce the pore size of the membrane, for example, for ultrafiltration, you probably have to add 1 more layer. For nanofiltration, you have to add another layer. So it makes the layer become more and more if you would like to reduce the pore size of the ceramic membrane. So the conventional way how to prepare the ceramic membrane is either by using a multiple step process like this one. So we have to have the powder mixed with some solvent, and we stir, ball mill to produce the ceramic slurry and paste. And after that, we can produce the support precursor. Okay, so how to produce the support is either by using tape casting, slip casting, or pressing. This one is to produce a flat sheet membrane. Flat sheet membrane is meaning that it's like a planar membrane. Okay, and if we want to produce the tubular membrane, we have to use the extrusion process. The tubular meaning that it looks like a straw, and the size is normally from 5 centimeter up to 10 centimeter the size. Okay, so you have to do sintering after you get the precursor in order to turn into a strong ceramic body, and after that, in order to alter the pore size of the membrane, so we have to do deposition technique. Either you can use vapor deposition or you can use coating, and followed by one sintering. And this process can be repeated depends on what is the pore size desired for your membrane. Okay, the smaller pore size that you need, so probably the more repetitions of this step you have to conduct it. Okay. So this is one of a few reasons why the ceramic membrane is expensive. Firstly, is because of ceramic membrane made from expensive material. Alumina and zirconia is very expensive. It's probably 10 times more expensive than the polymeric material. And also the step to produce this asymmetric structure is also multiple steps. I just showed to you just now. So we have to do the extrusion, sintering, deposition, sintering, and followed by a few more steps in order to get the desired structure. And also the high temperature sintering for the commercial material like aluminum and zirconia. Okay, so that's make the energy consumption process to produce the ceramic membrane. And also the configuration for the current ceramic membrane. Normally you can find either as a flat sheet or tubular, they're commercially available. And these types of configuration lead to the relatively lower surface area. So therefore, the strategy to produce or to reduce the cost of the ceramic membrane has been proposed by many researchers. You can use the alternative material that are readily available in low cost to replace alumina and zirconia, or actually we can also use the phase inversion technique to produce asymmetric structure in a single step. Okay, I will talk about it later. And by using this phase inversion, you can produce a structure what we call as hollow fiber. This is some picture of the hollow fiber. The diameter is about 2 millimeters, and we can increase the surface area of the membrane by having this types of structure. So this is the dry jet wet phase inversion sintering technique. Okay, the technique that now is emerging to produce the hollow fiber membrane. So by using this technique, you have to follow the first step is to prepare the dope suspension preparation. And after that, you get the suspension, you extrude through the syringe pump, through the spinneret, and travel some air gap before it reach to the coagulation bath. Okay, the external coagulant, normally we use water. So this is where the place the solidification process from liquid to become a solid will happen. Okay, so because of this process, this is what we call as the solvent-non-solvent exchange that lead to the solidification process we call as the phase inversion. This phase inversion normally can produce a symmetric structure, what we call as the asymmetric in a single step. So the asymmetric composed of the microvoids. Normally the structure is like a finger. That's what we call as a finger-like structure. And on the outer, there is a sponge-like structure. Okay, so this precursor, because of it also contains some binder, normally we use polymer as a binder, so we have to sinter them. So during the sintering process, most of the moisture, most of the retain, water, polymer, and other impurities will burn off, and what left is pure ceramic, what we get after sintering process. So if you look at the publication trend over the years, from 1969, the hollow fiber membrane is not really new. It has been invented a long time ago, but the publication is very, very slow until the phase inversion technique has been proposed to produce the ceramic membrane since the early of 2000. So you can see here from the early of 2000, the publications of the hollow fiber ceramic membrane has been increased tremendously, okay, for the past 20 years. So it's also proud to share that UTM, especially MTech, is the main contributor in the world nowadays in this area. So we are the leading institution for ceramic hollow fiber membrane. So if we can use these applications of the ceramic membrane, we can subject them to numbers of applications. For example, for water and wastewater treatment, since a ceramic membrane in nature is hydrophilic, so therefore it's very suitable to be used in water and wastewater treatment. Because of when it's hydrophilic, we can capture more water and it can produce higher flux. for the membrane. So therefore, the ceramic membrane is very suitable to be used for water and wastewater treatment. And we also can use it for the gas separation. Either it is based on the molecular sieve technique or the membrane protector. We have tried in fact to use this ceramic membrane for gas separation. And in fact, we can use it for the fuel cell as well. Okay, we can use it for fuel cell. So we're going to talk more about fuel cell today, as the topic for today is for fuel cell. Okay, so the ceramic membrane is very suitable to be used as the fuel cell material as well. Okay, now let's have a look at the more detail about the ceramic membrane application in fuel cell. Okay, what makes this fuel cell is promising option? Okay, people probably have heard fuel cell is a green technology. Yes, it's true, it's green technology. So therefore, we can use the fuel cell to reduce the dependency to fossil fuel in order to combat excessive greenhouse gas, which lead to the climate change. Climate change is not myth, it's a real global phenomenon. So because of the fossil fuel burning, so we release a lot of greenhouse gas, and this greenhouse gas will make our world hotter, and therefore it can risen the seawater level. Okay, how the seawater level can be risen due to the global warming is because of the melting of the ice sheet and glacier that added the water inside the seawater. Okay, and also the expansions of the seawater when the temperature is hotter, so the water molecule become more active and is expand a little bit. So therefore, the seawater will rise. And based on the data they obtained from NASA, so we can see that the increase of the seawater is quite high, 3.3 millimeter per year. Just imagine how this increase in 100 years, in 200 years. So it will reach, and it will probably cause many cities not exist anymore. Okay, so therefore we have to take some action how to combat this climate change issue. So if we compare the fuel cell with the combustion system normally we can see most of the electricity in Malaysia, I can say like more than 50% of electricity in Malaysia is based on the combustion system. Either it's from coal or it's from fossil fuel or other types of fossil fuel or biomass and so on. Okay, so this combustion system, it's involved a multiple step process, meaning that you extract any chemical energy from the fuel, but you not convert to the electrical energy directly. Instead, you have to convert them into the several types of energy. For example, thermal energy, mechanical energy, and eventually you can convert them to become the electrical energy. But just imagine, because of the few steps of conversion, it will causes the losses of the energy in between before it can convert directly into the electricity. So this combustion system also will produce a lot of toxic gas like NOx, SOx, and particulate. And due to the many conversion, it normally has quite a lower energy efficiency. Okay, energy efficiency. On the other hand, for the fuel cell, it converts the chemical energy directly into the electrical energy. So if you imagine here, for example, we have the chemical energy of hydrogen, 144 megajoule per kilogram. If we can convert directly with the highest efficiency, so definitely with the 1 kilogram of hydrogen, for example, we can produce a lot more energy compared to the combustion system. It's because of the fuel cell convert the chemical energy directly into the electricity. And if you use hydrogen as the fuel, definitely you can get zero emission. You produce only water and heat. It is a zero emission. There is no CO2 at all. And the conversion is very efficient. Therefore, it can achieve 60% alone without the hybrid with the other types of technology. If you hybrid with the turbine, for example, you actually can further boost the efficiency up to 70 to 80% of the conversion. So when you talk about the fuel cells, there are several types of fuel cells. Okay, you can have the proton exchange membrane fuel cells, direct methanol fuel cells, microbial fuel cells. So these types of fuel cells use polymer electrolyte membrane fuel cell. You have alkaline fuel cell, which use alkaline as the electrolyte. You have phosphoric acid fuel cell, which use immobilized liquid phosphoric acid as the electrolyte. You also have the molten carbonate fuel cell, use molten carbonate as the electrolyte, and you have solid oxide fuel cell, which use ceramic as the electrolyte. Okay, so normally the classifications of the fuel cell is according to either its electrolyte. Okay, for example, like this one, you can see the name is according to the electrolyte, but the first three actually is according to the types of the fuel that use. Okay, for example, proton exchange membrane fuel cell, they use hydrogen. Direct methanol fuel cell, direct methanol fuel cell, they use methanol. For microbio fuel cell, they use wastewater as the feed. Okay, so these three is depend on the types of the feed that injected as the fuel. So for this talk, I would like to focus more on the solid oxide fuel cell, because the solid oxide fuel cell is the only fuel cell that use ceramic material as their membrane, as their electrolyte. Okay, so what is the solid oxide fuel cell? So normally the solid oxide fuel cell, the operating temperature is from 500 to 1000 degrees Celsius. Because of its ceramic material, therefore it can withstand at high temperature operation. And therefore you don't have to use a noble catalyst like platinum or any types of expensive catalyst like palladium as well. So by having solid oxide fuel cell, actually we can use cheaper catalyst because of high temperature. Therefore, normally at this temperature, the catalytic activity is more efficient. And due to its high temperature as well, fuel cell is flexible in the fuel selection, meaning that you not only use hydrogen as the fuel, but you also can use the natural gas, the coal gas and biogas as the fuel. Many types of gases can be used as the fuel for the solid oxide fuel cell. And also, due to its high efficiency, therefore it has a low emission, especially if you use hydrogen as the fuel. And due to electrolyte is solid, ceramic, so therefore you don't have any corrosion issue. You don't have any catalyst sweating problem like the other types of liquid electrolyte. For example, molten carbonate, phosphoric acid, they have such issue in their operation. And also these types of fuel cell also can tolerate for the impurities, meaning that if you have CO2 or if you have CO or if you have any contaminant in your feed, in your fuel, so it still can tolerate to these impurities. So this is how the solid oxide fuel cells work. So it's similar like other types of fuel cell or battery. It has three main components. So we call as the cathode, anode, and electrolyte. Okay. So the oxygen normally from the air will react with the electron, and it will break down into oxygen ion. This oxygen ion will travel through the electrolyte because the electrolyte has to be oxygen ion conductive. And when it's reached to the anode, it will react with the fuel, and after that, it can convert the fuel to become electron and also H2O. And because it is exothermic reaction, so it will release some heat as well. So the product from this reaction, if you use hydrogen, it is a purely H2O. And also because of the movement of the electron from anode to the cathode, so it can produce the continuous electricity as long as the feed been supplied. So the main character or functions of the electrolyte, it has to be ion conductive, and also it has to act as the separator between the fuel in the anode and oxidant in the cathode. And the characteristic of the good electrolyte, because this electrolyte normally we call as a membrane as well, so it has to be excellent ion conductivity. It is one that has to be excellent ion conductivity. It has to be thin, and also it has to be dense and gas tight. Okay, it has to be dense and gas tight, so that the gases from both anode and cathode will not mix together. Therefore, it must be gas tight and dense. So the normal configurations of solid oxide fuel cell, it has to be electrolyte supported. It can be found as the electrolyte supported. Okay, meaning that the electrolyte is the thickest part. okay, or it can be found as the anode supported. Okay, anode supported meaning that the anode is the thickest one, and the cathode supported meaning that the cathode is the thickest part. Okay, so but the most common configuration is the anode supported because of normally the anode material, nickel or nickel oxide as the precursor material for fabricating the anode is the most cheapest material compared to the material for electrolyte and cathode. So therefore, having the anode as the thickest part, so we actually can reduce some costs for the electrolyte and cathode because we use a very small amount of them. And also because of this anode supported, it can reduce the ohmic resistance, which come from the thick electrolyte. If you have a thin electrolyte, so you can reduce the ohmic resistance. Okay. And the configurations of the SOFC or the types of SOFC you can find as a planar as a sheet, or as a tubular. Tubular is like a straw. The diameter is from 3 to 10 centimeter, or it can be found in a smaller version, what we call as the microtubular. So this microtubular, normally the size is lower than 5 millimeter. So this microtubular actually have the advantages of all for the tubular, but on top of that, it also can produce a higher volumetric output, a quicker startup capability, good thermal cycling, and as well as the portable characteristic because of the small. And for information as well, why I showed in the previous slide, in the earlier slide about the hollow fiber membrane, is because the hollow fiber membrane, the structure is similar, exactly like the microtubular SOFC. So where this solid oxide fuel cell can be applied? So we can apply it for the stationary, for example, in the residential area, or in the biogas plant. For example, in Indonesia also, you have a lot of palm oil mill effluent that produce biogas during the treatment of the wastewater. So this biogas actually can be converted into the electricity by using solid oxide fuel cell and can be used for the inside the plant. Okay. And we also can combine them with gas turbine. As I mentioned earlier, the solid oxide fuel cell is exothermic reaction and produce a lot of heat. Okay, therefore, we can combine them with the gas turbine in order to boost up the efficiency of the energy production. And this can replace the combustion system. And if we can produce a small size, in fact, the solid oxide fuel cell can be used in a mobile application. For example, we can use a liquid fuel to power some small equipment like laptop or the light and so on. Okay. This is the commercially available solid oxide fuel cell for residential application. Okay. So you can see here from the left side, it is the planar solid oxide fuel cell. The power is like 1 kilowatt. This can probably power up the half of the house. Okay, the half of the house. Okay, and in fact, on the right side, okay, on the right side here, we have the solid oxide fuel cell that combined with the heat and power. And also this is an supported tubular cell. Okay, this can produce 0.7 kilowatt, okay, of electricity. So by having these small versions of solid oxide fuel cell, actually we can power the whole house. Okay. And the good thing about fuel cell as well, you can scale it up. Depends on the desired output unit. For example, one size of SOFC here, you can generate 100 kilowatt of electricity. So if you like to have a 500 kilowatt, you just install a 5 unit of the same SOFC system like been done in the eBay headquarters. Okay. And in fact, like I mentioned, we can use it for portable. So this is the example of the portable SOFC where we just power them by using propane. Okay, so you can use it for the ground sensor, for the unmanned aerial vehicles, and also for the robot pickers. And in fact, it can use for LPG as well. And we can use it for the military mission and also of grid power for the electronic, radio, and also computer. Okay, so I tried to take another 10 to 15 minutes to just give some overview about the microtubular solar cell fuel cell, especially on the research that has been conducted in ANTAC. So, like I mentioned, hollow fiber membrane is similar structure as the microtubular solar cell fuel cell. So the diameter is 2 to 3 millimeter only. Okay, so we can use in between 500 to 1000 degrees Celsius. Okay, so if we choose to operate 500 to 700, meaning that it is in the category of the intermediate temperature, so we can use the gallium cerium oxide CGO based electrolyte. It depends on the types of material. So if you would like to use a temperature 700, so we can use different types of material like the yttrium stabilized zirconia electrolyte. Okay. So this is the conventional way how to produce the microtubular solar cell fuel cell. Okay, we have to produce the support. For example, we have the anode as the support by using phase inversion, for example, or ram extrusion, for example, and we have to sinter them, and we have to deposit the second layer, for example, the electrolyte, and sinter them again, and we have to deposit another layer like a cathode and sinter them again in order to get a complete fuel cell. Okay, but we actually introduced a technique to produce a fuel cell in a single step, meaning that we can produce a 3 component simultaneously by using co-extrusion technique. By having this technique, we can save a lot of production costs, promote the great adhesion between the layer, and we can reduce the defect on the fabricated membrane and also shorten the production time. So this is the step similar like we produce the hollow fiber membrane. First is the phase inversion based co-extrusion technique. Instead of having a one ceramic suspension extruded through the spinneret, but if you would like to have a 2-layer or 3-layer, so you have to multiple it. Okay, meaning that you can inject the electrolyte layer and also you can inject the cathode layer simultaneously in order to produce the triple or dual layer. So this is the spinneret that we have for orifice spinneret in order to produce a triple layer hollow fiber membrane. And before we can co-sinter them together. And by having this step, we only need to use one sintering process. So in order to test the membrane or the fuel cell, so we have to make into a reactor and assemble them. We have to connect with the silver wire as the current collector and so on before we insert into the furnace, and we can measure the power density of the membrane of the fuel cell. So in MTech, this is the some evolution that we have done for research of solid cell fuel cell. So we started for the first 3 on the dual layer hollow fiber membrane, and the phase 4 we moved to the triple layer hollow fiber membrane, and the phase 5 we try to use methane as the fuel. For the first 4 we use hydrogen only, but for the last one we try to use methane to prove that the microtubular solar cell fuel cell also can use using the hydrocarbon fuel. So for the first phase, okay, so the objective is to produce a defect-free hollow fiber dual layer hollow fiber membrane, which consists of the electrolyte and anode. And this is the fixed parameter that we use for anode and electrolyte. And in terms of the structure, by using the dual layer, it has advantages because it can produce a very great adhesion between the layer without any delamination. The issue with the ceramic material, especially for the multi-layer, is always associated with the delamination, meaning that the inner and outer have a different thermal expansion, and therefore it can create some crack. But because of we use the same polymer binder and the same solvent, so therefore the interface between the layer is seamless, meaning that we cannot see difference too much between the electrolyte and anode layer. So the electrolyte you can see here is much thinner than the anode layer. Okay, and the anode layer you can find there is some finger light. That's what we call as the asymmetric structure. So from the dual layer, in order to get the data for the complete fuel cell, so we have to add it with the cathode layer by using a brush painting technique. So this we use it manually, and before we sinter them at 1200. Okay. So we measure the fuel cell at temperature from 550 to 600. And what for fuel cell, what is the most important thing to be seen from the result is first is the maximum power density. Maximum power density is the multiple of the voltage and current density. We can get the power density. So you can plot this data. Based on this data, the maximum, the highest peak is what we call as the maximum power density. And the open circuit voltage is where we can get the voltage when there is no current to be withdrawn from the fuel cell, meaning that the fuel cell is still disconnected. So we can get the open circuit voltage. So the theoretical OCV, open circuit voltage for fuel cell, is 1.1 based on the Nernst equation. Okay, but we got here is almost 1. So meaning that this indicates that the electrolyte that we produce is quite dense enough. Okay, so if we look here, the power density that we produce at the highest temperature, 600, is 0.69 watt per centimeter square. So this temperature, if we compare with literature, is still quite low. So we try to find an alternative, how we can further reduce, further increase the power density of the fuel cell. So because of the higher the power density, the better the performance of the fuel cell. So we try to reduce the thickness of the electrolyte. The good thing about the co-extrusion process, we can adjust the structure and the dimensions of the fuel cell accordingly. So if we want to reduce the thickness of the electrolyte, so we can alter the extrusion rate from 5 up to 0.5 ml per minute. Okay, so by having the variations in the outer layer extrusion rate, we actually can produce a different thickness of the electrolyte. So we can vary from 7 micron up to 10 micron of electrolyte. Okay. So by further reduce the electrolyte, okay, we can increase the power density to 1.11 watt per centimeter square. Okay, this is because when we have a thinner electrolyte, so the oxygen ion that transfer from cathode to the anode will have a shorter distance for traveling. So we can produce a lot more oxygen ion in the anode, and we can react with the fuel, and therefore we can produce more electron. Okay, when the more electrons produced, meaning that more power can be generated. So because of based on the comparison with literature, so our performance is 1.11, is a little bit reduced compared to the literature. In fact, so how to further reduce? We can alter the anode structure. Okay, we alter the anode structure by mixing the ethanol and the NMP as a solvent in our dope suspension, because ethanol is considered like a poor non-solvent. So the increase of the amount of the ethanol in the solvent will increase the viscosity of the suspension. So when the viscosity increased, so the phase inversion will not likely to be happen, or it happened, but it's very on the small part. Therefore, when you increase the ethanol content in the dope suspension, you can produce a shorter finger light compared to the one that you put a higher amount. Okay, you put higher amount. Okay, when you have a bigger or smaller finger light in the anode, actually it can act as the hundreds microchannel inside the anode, and therefore it can improve the fuel mixing and the diffusions in the anode triple phase boundary. Triple phase boundary meaning that the location where the fuel, the oxygen, and the electron can travel and transfer to each other. So if you have a higher triple phase boundary, meaning that there's more likely for the higher power to be generated. Okay, so when you have this one 70% of the finger light from the total cross sections of the membrane, so you can further increase the power density up to 2.3p. So this is actually the highest that has been reported in literature for microtubule fuel cell. And we also try to fabricate the triple layer hollow fiber membrane. But for this one, we use it for higher temperature. We use yttrium stabilized zirconia or Ag as the electrolyte. So we fix everything and we try to vary the sintering temperature from 1300 up to 1450. So T1 is for 1300, T2 is for 1350, T3 is 1400, T4 is 1450. So you can see that the structure is almost the same, but in terms of the densification, it's become denser at high temperature. So the mechanical strength is also increased, and the thickness also becomes shrink because at high temperature, the grain become closer and it shrink to each other. So because of for T1 and T2, we sinter at lower temperature, so therefore the ceramic hollow fiber is quite brittle. So we can perform fuel cell tests on such samples. So we only tested it for T3 and T4. So we produce a data 1.05. And if we compare with literature, ours is a little bit much higher compared to the literature that have the same operating temperature. Like you can see here, Young et al. 2009 at 700, they produce 1.03. On the other hand, ours is 1.05. So ours is a little bit higher for the similar similar operating temperature. Okay, in fact, our power density is also much higher, 0.75 compared to them 0.29. Okay, this is because of what? When we produce by using a phase inversion co-extrusion process, we can produce a tight electrolyte, and also we can have a very seamless boundaryless layer between the anode electrolyte and cathode. Therefore, when the oxygen ion or the electron want to jump from one side to another side, so they don't have any resistance because it can jump very smoothly. So lastly, we try to use the dual layer hollow fiber membrane with different electrolyte thickness, and we tested with methane as the fuel. Okay. So this is the thickness when we vary the extrusion rate from 0 to 5 mil per minute. So we can also get a various electrolyte thickness. So we apply for the hydrogen, we compare with the methane. Okay. The result has some trend, but it's not fantastic, I can say to you. For the hydrogen, we can see that the cell with the thinnest electrolyte have the highest current density. The thickest electrolyte have the lowest current density, and the performance is stable throughout the time. Okay, meaning that it can operate at longer time for hydrogen. But when you use methane as the fuel, so you can see that the thinnest electrolyte have a shorter lifetime. It drops very fast, and it can extend a little bit the lifetime when you have a thicker electrolyte. Okay, so this is because of the carbon deposition happen and take place when you have the methane. Because normally for the anode you use nickel, so nickel is very prone to the carbon deposition when you have the hydrocarbon fuel as the feed. Okay, so when you expose to the hydrogen, so the structure is still the same because there is no carbon deposition. But when you expose to the methane, so the carbon deposition will take place, and it will cause the structure changes on your electron anode, and therefore it will cause crack on your cells. Therefore, after a few hours, your performance is already dropped. So this is some strategy that has been reported in literature, how to reduce the carbon deposition. Either you can use reforming, or you can use add some impurities to the fuel. Instead of you use 100% hydrogen or 100% methane, for example, hydrocarbon, for example, you can add some oxygen source, but not too much, because if it's too much, it will create explosion. You can add some more, or you can add some mix with the hydrogen sources as well. Or we can replace or composite the nickel with the alloy or cerium oxide. Or alternatively, we can change the nickel directly to the titanates, bromates, manganetes, or vanadiates, okay, as the alternative anode material. But these types of material are normally more expensive than the nickel type. That is another limitation. So as the conclusion, what I can say from my experience, the fuel cell can offer a wide range of application because of its fuel flexible, not like a proton exchange membrane fuel cell. Proton exchange membrane fuel cell can only use hydrogen as the fuel. But for solid state fuel cell, you can use many types of fuel cell. In fact, you can turn carbon monoxide into energy by using solid state fuel cell. And therefore, it can be further enhanced in terms of the energy conversion if we combine with heat and power system. And for SOFC also, we can generate higher electricity if we combine with the turbine. Okay. In terms of the co-extrusion process, it can simplify the fabrication process and can reduce the production time and also cost. And by using this technique also, we can improve the structure of the membrane that can further enhance the performance by adjusting its parameters and adding some additive material to the electrodes. Some future directions, this is very short one. So if you would like to focus research on fuel cell, for example, especially solid oxide fuel cell, so this is the area that we can further improve. For example, to increase the lifespan of the SOFC and how to reduce its capital costs, and also the developments of the hybrid technology fuel cell with the turbine. And also we can further reduce the temperature of SOFC. For example, now normal operation probably from 500 to 1000 degrees Celsius, but if we can further reduce up to 300, it can be more interesting and promising technology. And also we can use the alternative anode catalyst to encourage the utilizations of the hydrocarbon as the fuel for solar cell fuel cells. And with that, let's thank you. I'm sorry for taking a lot of your time. So over to you, Dr. Trianda.
Okay, thank you very much for your impactful lecture, Professor Hafiz. Actually, you still have 2 minutes, so it's still on the schedule.
I tried to talk very fast in order to catch up with the time. Sorry.
Okay. I hope everyone enjoy and have a glance about the progress in membrane ceramic for fuel cell application. So that is the lecture from Professor Hafiz. Now we move into the next session, which is Q&A session. If all of you have any inquiries regarding the today's lecture, you may ask directly to Prof. Hafiz by using raise hand feature. So actually, in this room, Prof. Hamzah already arrived. Maybe Prof. Hamzah want to say hello to Prof. Hafiz.
Yes, hello, Prof. Hafiz.
Hello, Prof. Hamzah, how are you?
I'm really sorry that my other activities has just finished. So,
no problem. Yeah. I understand.
Actually, it's to be stop at 10 o'clock, but you know, some things happens.
No,
but thank you very much for your very interesting speech. Yes, please, students, you can could ask questions to Professor Hafiz. And Pak Trianda, please go once to host.
Okay, thank you, Prof. Hamzah. Maybe I will ask first, Professor Hafiz.
Yeah, sure. Okay. Okay, Prof. Hafiz, you have a very outstanding research on this SOFC. And it is interesting that in the SOFC, the thickness of the membrane also affects the energy density.
I'm also curious, what is the other electrode, or maybe the ideal electrode for the conducting the SOFC device, or is there any limitation on the membrane thickness, or maybe we should at least do it in the range of something to something? Is there anything like that? Okay, thank you.
Okay, thank you, Dr. Trenda. So yes, as you can see from the presentation, so the electrolyte give very huge impact to the power density as well as the OCV. Okay, so how this electrolyte can play roles is because electrolyte is the barrier between the anode and cathode. Okay, so it acts as the medium for the oxygen ion to transfer from cathode to the anode. So the thicker the electrolyte, so meaning that the more distant for the oxygen ion to travel from cathode to anode. So it will reach anode longer time if we have a thicker electrolyte. Okay, but if we have too thin, on the other hand, we sacrifice the gas tightness properties of the electrolyte. Because we have to bear in mind, electrolyte act as a barrier so that the fuel and oxygen don't mix together. So if the electrolyte don't serve as the gas tightness layer, it will cause the hydrogen or the fuel or the oxygen to cross over. Okay, so this will reduce the OCV, or open circuit voltage. Okay, so therefore, to answer your question, what is the ideal thickness of the electrolyte? Is normally, I can say, must be 10. We have produced 10 micron. It's good, but the OCV is quite low. The highest one we have tested with 100 micron, 80 to 100 micron. It is gas tight, but in terms of the performance is quite low because of too thick. So the ideal is from 15 to 30 micron, I can say. Yeah, because of this 15 to 30 micron, it is quite gas tight, and at the same time, it's going to be considered as quite thin as well. Yeah. So we have tested 15 to 30 is the ideal range of the electrolyte. Yeah.
Okay, I see. So it is 15 to 30 micron.
Micron, yes.
Yep. Okay, thank you very much. Okay. So maybe there is another question. Okay, one more for Hafiz. The SOFC operation condition is quite at high temperature, right?
Yes.
It's in the number of 100 degrees Celsius. If we look at the electron properties itself, when we exposure it into a high temperature, usually the electron will have high repulsion to each other. Thus, it will create another resistance that will lower the energy density. Is there any technique how to, yes, it is still a challenge, but is there any technique to hindrance this condition?
The trainer, can you repeat your question again? Sorry.
Yeah, because the operating condition of SOFC is quite high. Okay. So if we look at the properties of the electron itself, when it exposed to the higher temperature, usually among the electron will have high repulsion. So it will lead into another resistance that will lower the energy density, I think. So maybe that's why on your last slide, the challenge is to lower the operating condition.
Yes. I agree with you. That's why for fuel cell, either as in the anode or cathode, one of the thing that we have to give a full consideration is how to retain or increase the electron conductivity in the anode and electrolyte. And also there is a further research on how to produce a good what we call as the connector to transfer the electron from the anode to the cathode, so that the electron don't stay at one place too long. Once they produce, they have to be transferred from anode to the cathode directly. Okay, so if they don't transfer, so like you said, it will have some evolution, and also it can reduce the power density as well. So, but if we keep the electron moving by providing a good pathway for them to hop from one side to another side, so they will keep moving, because there is a driving force from the anode to the cathode. Definitely that is the driving force, because of the different charges of the anode and cathode that cause the electron to travel from anode to the cathode.
Okay, so it is basically to manipulate the electron density in cathode and anode. So it will make a differential in the electronegativity, right?
Yeah,
to make electron
that is
more.
why in the electrolyte, the nickel, apart from providing site for the reaction as the catalyst, but nickel is also a good electron conductor. So therefore, although this nickel, sometimes people try to replace them with the other material, but although it's good as the catalytic activities, but sometimes it reduces the electron conductivity. So it will create another drawback for the QSO. So therefore, the nickel, there is some threshold minimum for the amount of nickel inside the anode in order to keep the electron conductivity of the anode at the sufficient value.
Oh, I see. Okay. So maybe that is about the electron. Anybody have another question? I'm quite understand a bit about SOFC, but it's still a very interesting topic and have a lot of challenge. I think
many students told me solid QSA is quite difficult to be understand, because it involves not only a fluid but ion, right? So and plus the ceramic crystal structure, so it makes some difficulty to understand.
Patrianda, may I ask questions to Prof.
Yes, please.
Yeah, Prof. Hamzah, yeah.
Yeah, I have to ask questions because there are a lot of questions or problems that we found in the ceramics, or in this case, solid oxide fuel cells. Of course, the technical problem is one thing that make us very difficult in doing research in the ceramic membrane. The first is we have to connect, we have to join, or we have different type of materials with different thermal expansion coefficient for samples. But the membrane work at very high temperature, so it is prone to a crack or the breaking of the breaking up of the membrane. That is the first technical issue that I think it's not easy to solve. Yeah. The second thing is we really want the membranes can last longer. If possible, it lasts forever. But the high temperatures also makes the situation is difficult, because the membrane is not single phase. Yeah, we have multiple phase inside the membrane materials, and at high temperatures they are reacting together. And then what is the what have we learned from the experience how to minimize that effect. Yeah. Okay. Please give some simple explanation. Because high temperature reactions means that we facilitate the solid reactions, and then as a prolonged time, the reactions will create or will make a new phase as not really wanted for the membrane. And that's it from me. Thank you.
Okay.
Bye.
Thank you, Prof. Hamza. Very interesting question. So regarding to the crack, that is one of the main challenge for producing multi-layer hollow fiber using co-extrusion process, because of some of the material has a different thermal expansion coefficient than the other material. For example, for anode, cathode, and electrolyte, if you extrude them together, so definitely you have to use a different material, because you need to have a different purpose of different functions for each component. Anode have a different function, electrolyte have different function, cathode has different function. Definitely you have to use a different material. If you choose a material have a two big difference in terms of the thermal expansion coefficient, definitely we cannot solve the issue for the cracking. So we have tested with a few material, for example, like BCZ1. We have used multi-layer. We have tried to perform many things, but it still cannot solve. Therefore, before we tested with the co-extrusion process, we have to check the thermal expansion coefficient and the shrinkage by using the latometer to check either this 2 or 3 layers have a too big difference in terms of the shrinkage during the heat treatment. So if there is, so it's hard to produce a crack-free hollow fiber, except one of the approach that we always use is to add some of the electrolyte material, for example, powder, inside the anode and cathode as well, like 50%. For example, 50% of the electrolyte material, YSZ, inside the anode. 50% of the YSZ also in the cathode, so that it can reduce the expansions of the other types of material if they're present. Okay, that is for the first question. For the second question, I totally agree with you, Prof. Hamza. Definitely, when we tested with the methane, we can see that the cell is not stable. We produce some crack. So this is happened because of there is a carbon deposition. So if I'm not sure, have you experienced with hydrogen before? But if we tested with hydrogen, normally the cell is sustained. You can produce quite a stable cell. But if you use hydrocarbon, or if you induce some carbon dioxide or carbon monoxide inside your stream, so because of the reaction between the carbon and nickel, if you use nickel-based material, so there is some carbon deposition will take place. Therefore, now we are investigating of how to cater or to tackle this carbon deposition issue. Many researchers also have studied to replace or to reduce the amount of nickel so that the carbon deposition can also be minimized.
Yeah. Thank you, Prof. Hafiz. Yeah, this problem comes when we use hydrocarbons. Yeah, sure. For hydrogen, it's okay.
Yeah, for hydrogen, definitely, normally, based on my experience, we don't have a very severe issue of cracking. But for hydrocarbon, normally, because of the nickel is prone to carbon deposition, so it will create some crack on the cell. But if we can replace with the other types of catalysts, so I think we can solve the issue. But sometimes the catalyst is also quite expensive, or it's cannot provide a good electron conductive, so that we create an issue that needs to be solved.
And the other thing as well, so when we work with ceramics membranes, is it is difficult to model it. So, for example, if you want to do calculations based on the quantum mechanics or based on the normal modelings in molecular level, it's not easy to do that because the system is too complex. Yeah, it's not only one clusters of metals in the cluster. It has more than one metals, and then it's very difficult to build the model to do the calculations. If it's possible, it needs, of course, larger computational facilities to do all the calculations. Thank you very much, Prof. Hafiz. Very interesting talk this afternoon. Ya, Pak Trianda, back to you.
Okay, thank
This is the question from
you, Prof. Hamza, and thank you, Prof. Yeah. Here, when I look at the Zoom chat, we have a question from Arif Priyangga. He is our doctoral student in our lab. I think Arif also have visited Amtech in the past and have a collaboration with Dr. Juana. Maybe Arif, you want to ask it directly to Prof. Hafiz?
Yeah, Dr. Tianda, if you don't mind, I will take it. Thank you, Dr. Hafiz. Sorry if I turn off my camera to stabilize my connection. First of all, thank you for your insightful presentation. It is very interesting. I would like to ask about the temperature issue in a ceramic membrane. That what is the highest temperature that you have applied to the membrane? What is the highest temperature? And what is the main factor that affect the stability of membrane related to temperature? Maybe the cracking of the membrane, and then the performance of the membrane in to the conduct.
Okay,
What
thank
is
you.
the effect of the membrane? And
you for the temperature, you mean is it the sintering or the operating temperature?
Operating temperature.
Okay, understand. Okay, to answer your first question regarding to what is the highest temperature can be applied to the membrane during the operation, it is related to the melting temperature of the material. So different material have a different melting temperature. For example, if the material have a melting point at 2000 degrees Celsius, okay. So for this case, normally we can operate because we can operate it before it can be sintered. Okay, normally the sintering temperature of a ceramic material is 70% and above from its melting point. So if there is a melting point at 2000, so the sintering temperature normally at 1400. So before that, you can use it. Because one it's have some sintering effect, so the grain particles will diffuse together and will change the structure of the membrane. So we try to avoid that during operation. So therefore, the ideally is 50% from the melting point. So like if you have the melting point at 2000, probably you can operate at 1000 degrees Celsius. Okay, so that will work fine before it's sintering process. So regarding to the second question, what is the main factor affect the stability of the membrane related to the temperature? I would like to get some clarification from you. So this membrane, you talk about the fuel cell or like the other types of application, for example, like gas separation or water treatment, because the stability is actually depends on the application as well. Arif, can you further clarify or enlighten us?
In fuel cell application.
Okay. The temperature if the temperature, like I mentioned, does not exceed than the centering temperature of 50% from its melting point, it worked fine. Okay, it worked fine. But if the temperature is too high, it will cause the grain diffuse together, and it can combine to become, just imagine you have this grain, right? So when at high temperature, it will close to each other. So it will produce a bigger grain. So when it's produced a bigger grain, so it will affect the structure as well as the surface area of the catalyst, for example, if we talk about catalyst. So this actually can reduce the stability of the membrane. Okay, so therefore you have to ensure that the operating temperature does not above than 50% of its melting point. Okay, and the main factor is really depends on the application and the types of the component. For example, the electrolyte probably different. The anode probably because at higher temperature normally, the anode, if we use a nickel oxide as the precursor, it can reduce into a nickel at high temperature. But just imagine for fuel cell, it's like other types of commercial system. Sometimes you want to turn it off. When you want to turn it off, it can back into the original form, nickel oxide. But when you turn it up, it will become nickel again. So this nickel oxide, nickel will further oxidize and reduce many cycle. Depends on the temperature, depends on the presence of the fuel. So this will affect the stability of the membrane because of the structure. Just imagine sometimes you shrink, sometimes you enlarge. Sometimes you shrink, sometimes you enlarge. So if this keep in many cycles, so there is a possibility that the ceramic component become more fragile from time to time. So it will create some crack over the time. Probably after a few months, after a few years, it will crack because of the different shrinkage and expansion mechanism. Yeah.
Thank you, Prof. Hafiz. It is clearly.
Yeah, welcome. Thank you.
And maybe there is the last question from me.
Sure.
If
No
you don't mind.
Yeah, no problem.
I know that in your early presentation that you mentioned about the asymmetric structure in your membrane, and I think my question is it always in asymmetric structure if we fabricate the ceramic membrane for fuel cell, or any kind of structure that we need to make a better performance for the membrane, and we can apply to the membrane that the performance is better than the asymmetric structure.
Okay, thank you, Ari, for very good question. So let me give some idea how the cells of fuel cell works, especially inside the anode. Yeah. Okay. Yes, I agree with you. Asymmetric structure is not the only structure that can be produced by phase inversion. Because phase inversion, like I told you, we actually can reduce the finger light or we can extend the finger light length. Okay, it depends on the parameters that we try to manipulate during the fabrication process. Okay, so but this finger light, the drawback actually is can lessen or can reduce the mechanical strength of the membrane, because the finger light is actually a defect. Okay, it's been called as a defect. This microvoid, so it can be called as a defect. So if you have too many defect, so it will reduce the mechanical strength. Okay, therefore you have to keep it in the ideal amount and ideal length for the finger light in order to produce a good flow of fuel. Okay. Why we need to have a finger light is because when we flow the oxygen, when we flow the fuel inside the anode, just imagine there is no finger light, there is only sponge-like structure. So probably only on the surface, because we don't apply too high pressure for the feed to travel inside the anode. We apply just nice pressure. So therefore, with the applied pressure, the fuel probably cannot reach up to inside the area in the anode. It can only reach to the outer layer, or probably up to few microns from the anode, from the surface. So when you have very small amount for the reaction to take place, so many of the anode area will not be utilized. Okay? So therefore, it cannot create a higher electron to be produced. Okay? But if you have the finger light, we expect that this finger light actually can have a vortex flow, meaning that it will go inside the finger light and it will disperse the fuel throughout its boundary, so the fuel can reach to more area in the anode. So by having these types of mechanism, we expect that all the area deep inside the anode also can provide some reaction. Okay, can also provide some reaction, and therefore it can produce more electron. Okay, so therefore we can have higher power density. So this is what we predict, we hypothesize, okay, from the structure. So this asymmetric structure is good, but it has some limitation in terms of reduce the mechanical strength. But I believe with you, if you can change the finger light into a better, bigger microvoid inside it. For example, if this pore can be further make it bigger, and there is a continuous pathway for the fuel to travel. So in fact, that is much better structure. But sometimes when you have a big pore, but if it is isolated, or we call as the island pore, so it will not be useful as well. Okay, so the useful pore, it has to be connected to each other. So how to make it connected is that is the tricky part during the fabrication process. Okay, thank you. I hope I answer your question.
Okay, thank you, Prof. It is clearly enough.
Okay, thank you, Prof. Hafiz, for your question, or for your answer. We have another question from Pak Wahyu. He's joining us from Hong Kong. Okay, hello. Please, Pak Wahyu.
Hi.
Hello.
Hello. Yeah.
Thank you for the opportunity. I am Wahyu. I'm a lecturer in the Department of Chemistry, but now I'm still pursuing PhD in City University of Hong Kong. And I'm quite interested in your...
Wahyu. Nice to meet you.
Nice to meet you too. Actually, we have ever met once when you first time going to Surabaya at that time. Maybe you forgot about that.
Yeah, I think I remember your name.
No, I need to use my mouse. Now I'm start to learn or study about the electron conductivity. Usually we study it, or at least I study it using the electron EIS analysis, and I also see from your slide and some of your publications that I think you have many publications which correlate with the electron impedance spectroscopy. And I'm still start to learn about this. And in this analysis, sometimes maybe my question is very basic or technical, but it's a great opportunity to directly ask to you. In some of your paper, sometimes when we do the AES analysis, we can get some value. For example, substrate resistance, transport resistance, or charge transfer resistance, and some other parameters. But maybe you have an opinion or you have an advice. For example, if we want to measure or analyze the electron conductivity in the thin films, I see one of your recent publications about the impedance analysis of charge transfer upon nickel doping in titanium-based flexible dye-sensitized solar cell. It is in this paper, it seems like you deposit the titanium-based catalyst in the surface of IGO, and of course you have some value for the impedance. I'm still not understand. Between all of this parameter, for example, substrate resistance, of course, we have the resistance from the substrate itself, the resistance within our catalyst itself, and maybe with the electrolyte. What's the main factor that we need to concern about when we do measurements?
Okay.
It's
Thank you, Wahyu.
Ah.
Okay, I can give you some idea that related to solid subfuse cell.
Oh, yeah.
Probably because I'm not very expert actually in impedance or electrochemicals, but I will give some sharing based on my understanding. Okay. So for the impedance, when you read the data from here, for example, so what you can get, because in fuse cell, there is three types of polarization that will take place. First is the ohmic resistance. Second is activation polarization. And thirdly is the concentration polarization. So based on the impedance, normally you can measure the ohmic resistance, meaning that coming from the conductivity. Ohmic normally is coming from the conductivity. Either it's come from the electrolyte, it's come from the anode, or come from the cathode. Okay. So when you see here, the first intercept of your impedance data actually is represent the ohmic resistance. Okay, this is the first intercept is your ohmic resistance. So ohmic resistance is come from the conductivity like two, anode, electrolyte, and cathode. But since we use a very, very good anode, conductive anode, because we use nickel, the conductivity is like 10,000 or more than that. Okay, and for the cathode also we use perovskite structure, which has a very, very good electron conductive material. So the only make it different and give a high resistance is the electrolyte. So if you have a multi-layer, you have to know which component have the highest resistance. So normally the highest resistance will dominate the reading for the ohmic resistance. Okay, for our case, from anode, cathode, and electrolyte will give the highest resistance because of the conductivity is much, much lower compared to the anode and cathode. Okay, therefore we look at the ohmic resistance here. The first intercept is the ohmic resistance. So another resistance coming from the activation polarization and also concentration polarization. Normally, if you can have a better equipment, you actually can find the two semicircle. Okay, it's very nice semicircle, semicircle. But because of ours, probably we have some issue with our setup, so we cannot measure the two semicircle very nicely. So you can see there is some shape, but it's hardly to be determined where is the second and third intercept. But the distance from the first and the last intercept, actually that one is the polarization that contribute by the activation and concentration. Concentration coming from the flow of the fuel and oxygen inside the fuel cell, and the activation is coming from the catalyst itself. So how efficient is the catalyst? So because the activation is from in order for the reaction to take place. So it really depends on the efficiency of the catalyst. I hope I can answer or give sharing more, but I have very limited knowledge on this. Yeah, so sorry about that. Yeah, but that's why for FUSA normally you will check the ohmic ASR and also electrode polarization for the intercept between the first and the last intercept. The distance is the electrode polarization that I mentioned, activation and concentration polarization.
Oh, thank you, Professor Hafiz. Oh, then I think indeed we need to consider about our system itself and our catalyst system itself, which may have a more influence in our system, so we can predict ourselves. I mean,
if you would like to measure the conductivity, I think the first intercept is the most important one. The distance between the axis and the intercept is that will indicate your conductivity. Yeah.
Thank you very much.
No problem.
Nice to see you again.
Nice to see you.
Okay, thank you for Hafiz for your answer, and Pak Wahyu for joining us from Hong Kong. I know it's a very long journey to get here. Okay,
Cannot
so
pronounce.
How long you have been there? How long? How long you have been?
This is my second year. This is my third year.
My
third year.
In Australia, yeah?
No, in
Hong Kong.
Hong Kong.
I heard Wollongong, something like that.
Oh,
Australia.
Okay.
All the best for your study.
Thank you. Hopefully we can keep in touch after this.
There's no problem.
Okay, thank you. So maybe that's it. Everyone, I know you still have a lot of questions in your mind, but unfortunately, the only thing that limiting us is time. So because the time is already up, so maybe I will call it a day for today's session. Once again, I'd like to thank to the Prof. Hafiz for your lecture today. It will is very interesting talk and a very interesting topic with full of very a lot of challenge to be solved. And I'd like also to thank to all of the participants who are still here, keeping their attention in this today's series. Maybe that's all for me. I will give it back to the MC, Pak Tamam. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you so much, Prof. Hamzah, Dr. Janda, and all. Thank you.
Thank you.
Thank you very much.
Jangan kapok ya, nanti akan ada lagi beberapa
Boleh
kali.
Pak, boleh. Boleh, tidak masalah.
Thank you very much to our speaker, Prof. M. Hafiz Dazan Otsman, who has give us knowledge. May it will be useful in our research. And thank you very much to our moderator, Dr. Trianda Gunawan, SSE. The last agenda is closing and prayer. Let's close the event by reading Hamdalah together. Alhamdulillahirrahmanirrahim. Thanks to our speaker, moderator, and all participants of the seminar present today. We will inform you that this seminar can see in YouTube, Faculty of Science and Data Analytics ITS. To commemorate our togetherness, I ask everyone to take a group photo. Please, all participants can turn on the camera. Operator, can help me? Ready, operator?
Siapa yang foto ini?
Okay, thank you, operator. Please give the best smell, right? 1, 2, 3. Cheese. Okay, thank you, operator. Thank you for our participants. Thank you for our speaker, moderator, and all participants. Thank you For all, finally, from the depths of my heart, I do apologize for my mistake in presenting in this event. Thank you very much for your kind attention, and thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi
Assalamualaikum
wabarakatuh.
warahmatullahi wabarakatuh.
Thank you.
Terima kasih Prof. Hafiz,
Thank you,
Pak Trianda, Badrut, Mbak Deti, Pak mahasiswa, Bapak Ibu dosen. Sampai ketemu lagi di lain kesempatan. Ya, alhamdulillah. Terima kasih. Saya izin leave ya. Silakan Pak Hafiz juga boleh.
Okay, thank you, Pak. Ya.
Sampai jumpa
Terima
lagi.
kasih, Prof. Hafiz.
Lagi, thank you so much.
Ya.
Lagi, Pak Trianda.
Mas Trianda, apa kabar?